Good day, everyone. Our topic for today is about uh, the cantilever beam with or without support at pre-end. So, this problem uh, is also in the reviewer book of a well-known, published by a well-known review center. So, here is the problem. A prop cantilever beam is 10-meter long. Its flexural capacity is 680 kN and its web shear capacity is 820 kN. Flexural rigidity of the beam is 65 times 10 to the 12 Newton millimeter squared. Number 1. Find the allowable load kilonewton per meter on the beam based on its flexural capacity. Number 2. Find the allowable load based on its shear capacity. Number 3, the prop is removed resulting to displacement at the pre-end of the beam. Find the camber required millimeter to offset the beam deflection at the pre-end. So here, the cantilever beam is prop or it has a support at the pre-end. So here, I will introduce to all of you my own formula that I invented way back in about 2018. So this is the formula in computing for the fixed end moment of the beam. It is equal to the uniform load or the uniformly distributed load multiplied by the length of the beam multiplied by the moment arm of the moment diagram of the beam all over the degree of the curve of the moment diagram. So, in I've been working on this formula way back in 2018, and uh, I started enhancing and improving it ever since until I already proved that this formula that I invented is correct and accurate. So, let's start with the solution. So, here we have the figure beam AB with A at the pre-end and B at the fixed end. So it has a uniformly distributed load with the length of the beam is 10 meters. So we are asked to find the allowable load in kilonewton per meter on the beam based on its flexural capacity. So the flexural capacity of the beam is here, 680 kilonewton meter. So first, we have to draw the moment diagram of the beam, assuming that there is no support at the pre-end. But actually it has a support, but we will just assume that there is no support at the pre-end because the support at the pre-end will be there. It will stay there, but it will not be included in the computation of finding the fixed end moment of this beam. So, finding the fixed end moment of this beam with support at pre-end. So, the moment diagram of this beam will be, or the uniform load, or the moment diagram of the uniform load will be this one. So, it will be a second degree curve. So, the moment diagram by parts of this beam is it is a second degree curve, and the moment arm is L over 4 or the length of the beam divided by 4 from the base or from the fixed end here. So if we are going to compute for the moment at B or the fixed end moment, so this is already the formula. We have here the uniformly distributed load multiplied by the length of the beam multiplied by the moment arm of the moment diagram all over the degree of the curve of the moment diagram. So we have here W, that is what we are looking for, and then the length of the beam 10 meters, and then the moment arm is L over 4 or 10 meter over 4 divided by the degree of the curve all over 2. So we have the flexural capacity here 680 kilonewton meter, is equal to, so simplifying this one, this 10 meter multiplied by 10 meter over 4 all over 2 is equal to 12.5 meter squared W. And we can get W to be 680 kilonewton divided by 12.5 meters, or W will be equal to 54.4 kilonewton meter. Okay. So this is the allowable load based on its flexural capacity. Okay. So the next question is, find the allowable load based on its shear capacity in number 2. So based on its shear capacity, uh, it will be 820 kilonewton. Okay. So, or that will be the shear at B, or shear at the fixed end. So, let's have the summation of moment at point A here at the pre-end is equal to 0. We will have the shear at B multiplied by the length of the beam is equal to, so the moment at B, wherein we have already computed 12.5 m squared multiplied by W, plus the effect of the load, W multiplied by L multiplied by L over 2. This is the formula for computing the load, or the uniformly distributed load. So, substituting the given values, we have 820 kilonewton multiplied by 10 meters. So, 820 kilonewton is the uh, allowable, the shear capacity in wave shear capacity of the beam. So 820 kilonewton multiplied by 10 meter is equal to, so 12.5 meters squared multiplied by W plus W of the uniformly distributed load multiplied by 10 meter multiplied by 10 meter over 2. So simplifying all the terms with W, we will get 62.5 meters squared multiplied by W is equal to, so 820 times 10 is 8,200 kilonewton meter. So W is equal to 8,200 kilonewton meter divided by 62.5 meters. So W is equal to 131.2 kilonewton per meter. So that is for number 2. And for number 3, it is just the usual formula. We will just use the usual formula in computing for the displacement at the pre-end if the support at the pre-end is removed. So the usual formula here, we will just use the usual formula here. Deflection at A, or at the pre-end without the support now, is equal to WL to the port all over 8 EI. So we have 54.4 kilonewton meter, multiplying that by 10,000 millimeters square to the port, because we must have the same uniform unit. So all over 8 EI, or 8 EI, 8 multiplied by 65 times 10 to the 12 Newton millimeter squared, and it will give us the deflection at the pre-end, or A, to be 1046.154 millimeter, or 1.046 meter. So if we are going to compare, we will just compare the solution in these reviewer books. So we have the same answer. We have the same answer. Sorry. We have the same answer, but with different solution. So it also has 54.4 kilonewton meter using their own solution, and I have used my own solution also, and it also has 131.20 kilonewton meter. So we'll just be focusing on the computation of the fixed end moment of the beam with support at pre-end. So this the answer here is also the same, but we will be just, as I've said, we'll just focusing on the computation of the fixed end moment. So we have the same W that we compute. We have the same amount of W. So to sum this up, I have here my copy of the formula that I invented. So this is the formula that I invented. So we have here, if you have a uniformly distributed load, so just draw the moment diagram of this beam, or the load of this beam, and then get the moment arm of the moment diagram and the degree of the curve. And so don't forget the formula to be the uniformly distributed load multiplied by the length of the beam multiplied by the moment arm if it is a uniformly distributed load, and divide that by the degree of the curve of this of the degree of the curve of this moment diagram. So that's all for today, and I hope that you learned something in our lesson. This is Engineer Armando Omanito, and until next time, and may God bless us all.